Now, the Milky Way is not only the home of our solar system, its importance to our existence runs much deeper than that. It is the birth of the sun and the planets of our solar system that could not have occurred without the galactic recycling that takes place within the disk of our galaxy and its interstellar medium. So there are new generations of stars that are made, and it's only that. So the new generations of stars was actually made possible by what we call the galactic recycling. And what do we mean by that? What happens in the interstellar medium, which is again the medium in between stars, there are different regions of the galaxy that change in composition at different rates, and that change in composition is because the heavier elements, heavier than hydrogen and helium, that are created inside the stars. And recall that the universe born with only hydrogen and helium. The rest of the stuff has been made by stars. So it took a first generation of stars that fused hydrogen into helium and then helium into carbon. Then especially the higher mass stars, they would fuse hydrogen into helium, into carbon, into oxygen, magnesium, silicon, and then iron. Remember, it was that core of iron that is going to explode, right? It's the dying stars. They're going to expel the gas, and in particular the newly formed elements, chemical elements, in that process that is called supernova, right? And that is hot. It's 10 to the 6 Kelvin. Those supernovae create bubbles. So let's actually go point by point now, by also and relating those with this nice image here. So what do we have? Stars live, okay? So there's nuclear fusion happening in the very course of these stars, and we see these are emission nebulae, stellar nurseries, newly formed stars here. And we see there are newly formed stars because there are large, hot, and therefore young stars. Young because they only live very short lives, right? So that means they die young. If we still see them out there, if we have evidence for those hot photons created by those massive stars, that means that only kind of happened yesterday. They're gonna die very soon, like tomorrow, right? Okay, of course, everything is in astronomical terms. All right, so now when they die, they explode, usually as supernovae, and they obviously return the gas into the interstellar medium, and there are stellar winds actually also associated with the giant phase. We talked about that, and they create the hot bubbles. How hot? The temperature is about 1,000,000 of degrees. Okay, so we can observe them in X-rays. All right, but those hot bubbles actually are going to cool in time, and that will allow the atomic hydrogen clouds to form. Okay, and these are basically the interstellar gas clouds in the plane of the galaxy. in the galactic disk, okay? And then further cooling, right? So here's what we have here. All these points, they are showing the direction in which gas cools for these points. So now we are at the atomic hydrogen clouds, or the interstellar material in the plane of the galaxy. Well, that needs to cool further in order to allow the atoms to stick with one another, and therefore form the molecular clouds. So here we had hundreds to thousands of Kelvin in temperature, but now we have further cooling, and now we arrive at just tens, around 30 Kelvin. And it's only now that gravity wins again, and now you had the newly enriched material. You have some of the heavier elements, but again mostly hydrogen and helium, and new stars are formed. And so there has been a steady element enrichment from 0 to 2%, right, over the past 14 gigayears. So when we say element enrichment, right, so we start with 0% of anything else, right? So start with only hydrogen and helium, right? So 0% everything else to 2% everything else. So things heavier than hydrogen and helium, but of course that means you still have 98% hydrogen and helium. We are a tiny part of that 2%, right? If it were not for this recycling of the gas, and of course we touched on the chemical enrichment, right? We would not have existed where we are now. Have any evidence for these things happening? Yes, we do, and this is just a schematic of what can happen with a young star cluster. And it's young because it has massive newly formed stars. It's kind of a redundant thing to say the massive stars, right? They're always going to be young. They live very short lives, right? So when we catch any massive star out there, it's very clear that it has been put together, was formed in the past a few 100,000 years, right? So that's, in astronomical terms, something very, very recent. Okay, and so they die, right? They're young, they're gonna live, and they die, explode as supernovae, right? So we're gonna have multiple supernovae coming from that young star cluster, and they're going to create the huge bubble, hot bubble. And how hot it is, that's temperature of 1,000,000 of degrees. Eventually, that bubble is going to cool down. So you see, like at the edge of it, it's already cooling, and they're going to basically rain back down on the disk, and that's because of the gravity of the disk. That will kind of call them back, right? So they're going to come back to the galactic disk. We have evidence for that. These are real observations. Of hot gas, that hot 10 to the 7 Kelvin in what we call a starburst galaxy, right? So this the rate at which stars are forming in the center of these galaxies is huge. And here's the X-ray image, and actually this is the X-ray emission. This is the correlation here, right? So X-ray, that means temperatures of 10 to the 6, that is millions of degrees, okay? Really, really hot stuff. And this is basically at the scale of a whole galaxy. This is where you see super strong galactic winds. These are real of this kind of phenomena. Now here's an interesting question. What do you think the gas will be in about 1 trillion years? What's a trillion again? Remember that 10 to the 12 years, so 1 followed by 12 zeros, whatever, however useful that could be for you, all right? Do you think that gas will be just blown out of the galaxy or still recycling just like it's doing it now? Or you might have guessed, because it's bolded here already, it's going to be locked into white dwarfs and low mass stars. And that is actually what happens, right? So it's not going to be blown out of galaxy because the disk and all the material in it still has pretty much the same mass, okay? And therefore, the gravity to basically call back everything that is blown away. So whatever is blown away is not going to have enough kinetic energy, enough power to go away from the gravity of the disk, and therefore gravity. And so the blown away material will eventually rain down to the disk. How about the other option? Will it still be recycling just like it is now? No, because new cycles of star formation, that means there are, remember, you go by mass and we have number of stars, and it kind of goes like this. So very few high mass stars that are formed, okay? But most of the stars are going to be the low mass stars. Most of them formed in a given cluster of stars. But the low mass stars, they live longer lives, right? Remember, the high mass stars live very short lives, right? This is actually what produces this recycling. So they live fast, they explode the supernovae, they return that all in enriched material into the interstellar medium, and then new generations of stars are formed. But the new generation of stars is basically going to have the same shape. You're going to have a lot of the low mass stars and very few of the high mass stars. And then again, new explosions. But in the meantime, it is these low mass stars, right? They're basically going to still be there while we create new stars, but at some point, right, there's not going to be new material to form the high mass stars because it's going to be basically locked into the low mass stars, or maybe not the very low mass, the ones that already lived and left behind after the planetary explosion, the planetary nebula explosion, left behind the white dwarfs. So I hope it was a good review of what we learned so far about how the stars form. Now a few words about the location, like where inside the galaxy we see stars forming, those star forming regions. And just as a reminder, those star forming regions are in the form of ionization nebulae or emission nebulae. They kind of look blue or reddish, and this is coming from excited hydrogen, ionized and excited hydrogen atoms, okay? And basically this is dust or gas, dust that's unveiling hot young stars, maybe like this. That emit those very hot photons that are going to be able to doubly ionize the oxygen. So basically you have maybe a tiny region here, and you spread the light, and you have the intensity here is a function of wavelength, and we look at all these features, and with some quantum mechanics we can actually figure out what kind of photons it took to create this extra emission, like on top of the continuum, right? So these are emission lines that we see here, and they are created by hot photons like UV, ultraviolet, created by massive young stars. And then the other type, or the reflection nebulae, which is basically gas that is around those hot young stars that is going to scatter the light coming from those stars. And that's material that looks generally bluer than the nearby stars. Okay, so just as a review, it's always a good review to see where actually do we see stars forming in our galaxy. And so basically ongoing star formation, well, that is revealed by either, remember, the presence of high mass blue stars. So you either see those stars or you see the emission nebulae or the reflection. Reflection, different kind of reflection. What did I do there? Okay, so you have basically gas that's ionized by light coming from the young stars, and we also have the dense molecular clouds. So all of these things show up basically in the plane of the galaxy. And here's how the plane of the galaxy, that line, that band of light, a band of milk, right, spilled in the sky. This is how it looks like in different wavelengths, actually. So we have here what you see in the visible. Okay, so that's the band of light, but this is at high resolution. So basically you see nothing, you don't see much. It's stars that are obscured by dust. right? So you don't see much. But then in infrared, you actually get to see through the veil of dust. You see those molecular clouds, that the dust that has been already heated up by those hot stars. Now in the far infrared, right, so longer wavelengths of infrared, you actually see the dust itself, right? This is the reprocessed radiation. The dust has been heated up and it emits its own radiation that reflects the temperature at which the dust has been heated up. And then you move to even longer wavelengths. So basically you have here the carbon monoxide emission. So this is in radio. We basically see the molecular clouds, the molecular hydrogen, but the molecular hydrogen doesn't emit, so we need to rely on proxies like emission from the monoxide carbon. All right, and then other ways of finding out just how much gas is out there. This is the basically atomic hydrogen that emits at the radio wavelength of 21 centimeters. That's atomic, and this is molecular, right? So different wavelengths in which you see things that happen in that disk of the galaxy. So now let's move to higher frequencies or higher energies. Basically, in X-rays, you're going to see the hot gas from the supernovae, and even higher energies. These are basically cosmic rays from supernovae and other highly energetic events, like maybe accretion in X-ray binaries, and just other types of collisions of the cosmic rays with atomic nuclei in interstellar clouds, as it's mentioned here. So basically we observe these. This is evidence, observational evidence for the star gas star cycle in multi-wavelength observations, right? So we have from the longest wavelength, so we have the longest here, to the shortest, the gamma rays, or the highest energy, right? If you are to, the energy increases this way. So we have energy of emission, and they're all present in the disk of the Milky Way.